The next form of a quadratic equation that we're going to graph is called the intercept form. Now, if you've watched the previous videos on graphing quadratics, we've graphed a quadratic function in standard form, and we've graphed a quadratic function in vertex form. And so this gives us a third method of graphing a quadratic function. And this particular type of quadratic function is already given to us in what we would consider a factored form. So if you recall factoring, we could take a quadratic that was in standard form and break it down into two simpler binomials, and then we now have it in a factored form. And what that gives us is that actually gives us the x-intercepts, and so thus it's called the intercept form. And so you can see here the form for intercept form of a quadratic. Now, more specifically, you need to know that the p and the q that are represented in here are representing the x-intercepts, and of course the x-intercept should always be written as a point. So p and then 0 and q and then 0, and of course the p and the q are both representing x values. We're just using a p and a q so that we don't confuse it with an h and a k, which represents a vertex, and we don't want to represent it just with an x1 or an x2, so because it may become confusing that way. So we use two different letters such as a p and a q. So these are going to represent our x-intercepts. Now, these 2 points, the p and the q in the intercept form, act similar to the h in the vertex form, where it's x minus p and x minus q, which is going to give us the opposites of those to get the p and the q value. Now, this is a little different from the standpoint of we're given 2 side points on the quadratic function by having the x-intercepts, but we still need to start off this process by finding our axis of symmetry and finding our vertex. So we can see very quickly, since it's a point on either side of the parabola, that it's going to give us an axis of symmetry that is halfway between those 2 points. So very important that you plot those 2 points first, find the axis of symmetry, and then we can go about finding the vertex from there. So if we take a look, as always, we have an a value as well, and if that a value is positive, it opens up. If it's negative, it opens down, and of course it acts the same way as it did in previous quadratic functions. So let's take a look at an example of an intercept form graphing example, and we got to go all the way down to example 3. In example 3, you can see that we have basically a quadratic that is broken up into 2 binomials. Now, the quickest way to recognize this as a quadratic is the fact that, remember, x squared is actually broken up into x times x. So since we don't have a squared term right here, we can still recognize the fact that we have 2 x variables in our quadratic, and since those would be FOILed together at some point to create a quadratic function, we can still call this a quadratic function because of the 2 x values. Now, we don't necessarily want to FOIL this together at this point because it's actually a little bit easier to graph this in intercept form than it would be to graph it in standard form. So we're going to take it how it is and use the 2 and the 4, or the -2 and the -4, to get our x-intercept. So the very first thing we need to do here is we need to identify our intercepts, and you can see that we want the opposite value. So we have a -2, and of course we're going to use the positive version of 4 for our p and our q, and then the a value in this case is represented by a -1. So we know that the parabola is going to open downward, and we know that it's going to be a standard shaped parabola since it is a value of 1. Now, the next thing we need to do is we need to take these P's and Q's and actually put them in the form of an x-intercept. So remember, an x-intercept is always written as a point. So we have our two x-intercepts. So that's the first thing that we can plot on our graph. So we're going to go ahead and plot the x-intercepts. One at 4 and one at -2. And this gives us 2 points on opposite sides, 2 symmetrical points on opposite sides of the axis of symmetry, which we haven't identified yet. But we know that the axis of symmetry must lie halfway between these, so we just need to do a simple count. So we see that that's 1, 2, 3, 4, 5, 6 units apart, divided in half. So the axis of symmetry should actually be 3 units from either point on the inside. So when we do this, we actually get an axis of symmetry of x equals to 1, and we can represent that with a dotted or highlighted vertical line. Now, we have the axis of symmetry, which is one of the things that characteristics that we always want to be able to graph. And then the second part that we always want to be able to graph is our vertex. And the way we do that is, since x equals to 1 on the axis of symmetry, that is the same value that x will equal in the quadratic. So we plug in the number 1 and y equals to 9, giving us a vertex of 1, +9. And we can graph that point. Now, this is a special circumstance where you have to make a judgment call. Normally, we would graph an additional point on either side of the parabola. But in this particular case, the vertex is far enough away from the x-axis that we get a definitive shape for our parabola, which does not require us to graph any more points using a t-chart. Now, if you really feel like you need an extra point to get a good graph, then feel free to go ahead and do one t-chart 1 point and then plot its point of symmetry on the other side to get your full parabola. But at this point, in this particular example, you're probably fine just leaving it with the 3 points that we have. So that's one of the nice things about the intercept form, is 2 of the points on either side of the parabola are already graphed for you. So now, we made mention earlier that intercept form is really just a factored form of a standard form of a quadratic. So if you ever wanted to put this in standard form, if we asked you for the standard form of the quadratic from an intercept form, all you'd really need to do is to use the FOIL concept that you learned before to multiply the two together. Now, if you like the intercept form better, and you're given a quadratic in the standard form, and if it can be factored, then you can actually put the quadratic in intercept form and graph it that way. So let's take a look at a couple examples on your own. We have sample problem number 3, part A and part B. Go ahead and pause the video at this point and graph those two samples. Check them in your graphing calculator and then see how you did, and then come back and watch the solutions to this particular set of sample problems. Alright, for sample problem 3, part A, we'll simply start by identifying the x-intercepts. And so in this case, our x-intercepts are written as points. So we have 3 for our P, so that's written as 3, 0, and 1 as our Q, which will be written as 1, 0. So we can go ahead and plot those 2 points, 3, 0 and 1, 0, and it becomes very clear that the point halfway between is at 2, so that is going to be where we're going to create our axis of symmetry. So our axis of symmetry is x equals to 2. So keep in mind, if you're being asked for the x-intercept, it should be written as a point with an xy ordered pair, and if you're being asked for the axis of symmetry, it should be written as an equation of a vertical line, which is x equals to whatever number represents the axis of symmetry. So to get full credit, you'll need to write it in those forms. Now, at this point, in order to finish our parabola, we're going to need to come up with a vertex. So for our vertex, what we need to do is, we know that the x value is going to be the same as the axis of symmetry, which is the 2. So we want to take that value and plug it in for all the x's in the quadratic function. And when we do this, we get a y value of -1. So in a y value of -1, that's going to give us a vertex of 2, -1, and we can plot that to -1. Now, here's a situation where in the previous example we told you that based off the distance the vertex was from the x-axis, that it was unnecessary for us to plot any further points to get a good idea of the shape of the parabola. But that's not the case here. In this particular situation, the vertex is up very, very close to the x-axis, and it is also very, very close to the two x-intercepts. So this is a situation where if I were drawing my parabola, I could go in many, many different directions. I could go straight up, I could go sideways. I can look here and know that the a value is equal to 1. So it's a standard shaped parabola, but it's still going to be a little bit difficult to draw with just these 3 points given. So this is a situation where it would be smart to t-chart just one more point. It's not necessary to t-chart 2 or 3 more points. And of course, I just need to pick one point to the left or one point to the right, because then I'll be able to plot the axis of symmetry point on the other side. So in this case, I'm just going to plot a 0. And if I put 0 into the given quadratic function, I'm going to get a resulting y value of 3. So 0, 3. And then of course, I have to plot the symmetrical point on the other side. And now I get a better view of the quadratic function being graphed. And so my parabola looks like that. So that is a good example of a quadratic function. Now, if you wanted to check this, you could check this in your calculator just by simply plugging in x minus 3 times x minus 1. And we'll take a look at that in a second. Let's move down to sample problem 3, part B, and take a look at that process again. So, again, we'll start simply with the x-intercepts, which in this case will be 1, 0, and then -1, 0. Remember that we're dealing with an opposite value with the p's and the q's. And if I were to plug those 2 points or plot those points, we could see very simply that they are on opposite sides of the y-axis. Now keep in mind the y-axis, which is representing our axis of symmetry here, would be represented by the equation x equals to 0. So it's very important that you understand that. And now we need our vertex. So our vertex would be an x value and a y value, and of course the x value is going to be 0, but we don't know what the y value is yet, so we're going to plug the 0 into our quadratic function, which gives us 2 times -1 times 1, and y is going to equal to -2. So now we have a vertex of 0 and -2. Now, in looking at this, our a value is a +2. So we know it's going to open up, but that it's going to be a little bit skinnier than your standard parabola. Again, my vertex is kind of close to the x-axis and doesn't give me as clear a picture of the parabola as I would like. So here it's probably a smart idea to go ahead and plot one more t-chart point just to get a clear picture. And in this case I'm going to use a -2. you could just as well use a positive 2. And when I plug in -2 for x, I'm going to get through my order of operations a positive 6. So that point's going to be a good ways up here. And of course I have the symmetrical point, which in this case will be 2 positive 6. And I have now a clearer picture of what my parabola should look like. Now, if I want to graph this in my graphing calculator to be able to check, I would simply punch it into my graphing calculator just as it shows on the problem. And then hit enter, and we can see that we've graphed it correctly. So that ends our lesson on graphing quadratics. If you've watched all of the graphing quadratics videos, we've now covered graphing quadratics in standard form, graphing quadratics in vertex form, and graphing quadratics in intercept form. You should know how to do each of these methods and the different parts that are necessary in doing the graphing procedure. If you have any questions, or if you're unsure of what you're doing, there is a document on Moodle called Graphing Quadratics Review, which shows all 3 methods and the different processes for each of them. So use that document to help you work through some of the practice problems.